Good morning, everyone. I am Longoria C. Platil, the presenter for our research entitled Multi-Criteria Evaluation of Pythagorean process sets from the viewpoint of set optimization. So let me share to you my screen. So on behalf of our study leader, Mr. Francis Adam S. Fuentes, let me proceed with my talk. Here's the outline. Now, being able to compare different entities is fundamental to decision making. For singleton elements, binary relations are already known to provide comparison and ranking among values. So, for example, those less than or greater than or equal to, we can use it to compare numbers such as 5 and 6 and 10 and 100. Set relations are then established to compare sets and has been widely investigated by researchers. So in this slide, some preliminaries are defined, Z being a real topological vector space. This denotes the set of all and empty subsets of Z. Set is a cone if this multiple, positive multiples of Z is in here. A cone is convex if this sum is in C for any Z1, Z2 in C. Transitive relation is induced by a convex cone C as follows. So whenever we see this, we can use this symbol to describe Z is inferior to Z prime if only if their difference Z prime minus Z is in C. So this is a partial order if it is anti-symmetric. Set relations are given as follows. So a set is inferior to another set B if only if all elements of this set is inferior to all elements of the other set. The others are interplay of the quantifier of A and B. So the weakest type of set relation is type 4. That is, A is inferior to B if and only if there exists at least one element in A such that it is inferior to at least one element in B. Here are some illustrations. So A here is inferior to B because every element of A is uh, smaller or lesser than B. And for the weakest type, at least one element here in A is inferior to at least one element in B. As a brief history, in 1987, these researchers defined 6 kinds of classification for relationships of sets. Around 2009, Kuano Tanaka studied unified discretization functions for sets. Recently, in 2018, Ike and Tanaka provided a new method of comparing fuzzy sets and introduced the notion of difference evaluation functions. So in mathematics, relationship for vectors is quite common or popular in vector optimization, and scalarization function for vectors is studied to determine how different they are or the magnitude of their difference. To generalize, relationship for sets was studied and their scalarization function for sets. And here fuzzy sets, which is an extension of our regular sets, uh, has been investigated. And recently, intuitionistic fuzzy sets, which is a more general type of fuzzy set, has been investigated. Fuzzy sets are used to deal with data that are imprecise. So for example, let G be a set of numbers close to zero. Let us define some fuzzy sets for G and show their membership functions. So there are many numbers close to zero, but if we give each number a precise grade, such as this function or this function, then we can see which are closer than the others. Note that the properties which a fuzzy set is used to characterize are usually fuzzy. Hence, we may use different membership functions to characterize the same description, but the membership functions defined are not fuzzy themselves. Since they are precise mathematical functions, we can say that nothing is vague anymore. This is the definition of an intuitionistic fuzzy set. So we have two membership functions, or the membership and the non-membership functions, which sums to less than or equal to 1. We can denote this set L as points alpha beta in this area, which sums to less than or equal to 1. Then we can denote IFS as a Z to L mapping. If the equality is strict or the less than is removed, uh, our relation is reduced to a classical fuzzy set when this is satisfied. The alpha cut of our intrinsic fuzzy set is defined by this. So, for example, if this is our fuzzy set, this one, then their alpha beta cut is this one. So these are now the some usual sets set with 3 elements and set with 2 elements. For convenience, we refer to the set valued mapping as the cut mapping of this. We define this as the partial order where this ordered pair is inferior to this pair if and only if component twice we have this relationship alpha 1 less than or equal to alpha 2, while beta 1 is greater than or equal to beta 2. It can be seen that this set is contained in this set whenever we have this ordering for any pairs in this area. This guarantees the monotonicity of the cut mapping of our fuzz. So here, we denote K as this yellow area. Then K intersection minus K is just this singleton set, hence pointed. And we have similar ordering here. A pair is inferior to this pair if and only if uh, this point is inside this alpha 1, beta 1 plus K. For subset delta in this area L, the sets of Pareto minimal points and Pareto maximal points are defined as follows. Every point of this delta is said to be dominated by a minima point if this is satisfied. And this is called the domination property with respect to K. Now, a more general type of fuzzy set, which is called a Pythagorean fuzzy set, is defined here. So this sum of the squares of the two membership functions is between 0 and 1. So we can see that the usual uh, facet is just this line, while the intuitionistic facet is this area. And the Pythagorean facets gives us a bigger scope. And the alpha beta cut of Pythagorean facet is defined similarly. This PFS is said to be normal if the alpha beta cut is non-empty for all alpha beta in omega. So omega is this larger area. We denote this as the set of all normal Pythagorean facets on Z. And now we introduce a new definition, which is Pythagorean facet relation. Pythagorean facet A is inferior to another Pythagorean facet B if and only if for all alpha beta in this delta, which is subset of omega, this alpha beta cut satisfies this set relation. From the definition, the following implications are obtained. So the strongest type 1, implies type 2, which then implies type 3, and which would imply the weakest type 4. This result is immediately obtained, as well as this one. And as a measure to determine how different those Pythagorean facets, we have this difference evaluation function, which is a mapping from this to the extended real numbers and given by the supremum of such t satisfying this one. An illustration and a proposition, this difference evaluation function is can be interpreted as a distance to move this set to an optimal position which satisfies the type 1 or the specific type of set relation. Okay. The next proposition provides alternative formula for the difference evaluation function when the domination property is satisfied. These concepts are needed to obtain the succeeding results of this study. These remarks are used, and then as an idea for two numbers AB, the order relation defined as follows: A less than or equal to B, if and only if the difference is non-negative. Similarly, the strict order relation less than is defined as A less than B if and only if this difference is positive. In this section, we extend such equivalence to the case of Pythagorean facet sets. So for type 1, given these assumptions, this Pythagorean facet is inferior to this Pythagorean facet, implies the difference evaluation function, the value is greater than or equal to 0. And a non-negative value implies this ordering. For the strict type, adding some assumptions here, we have this one implying a positive difference evaluation function. The converse is true without needing to have additional assumptions. So if the difference evaluation function value is positive, then we have this PFSA is inferior to P. For the other types, we have to use this lemma and also this one to have a similar ordering for type 2. Different assumptions, but this object is inferior to this object implies a positive differential evaluation function. The converse is true when this is delta compact. For the strict type, okay, we have this interior and the positive difference evaluation function value, and the converse is true. Combination of these two leads us to the type 2U, and combination 2L and 2U leads us to this type 2. This lemma is needed to prove the type 3 here, type 3L. Type 3 is analogous with different assumptions. Then the combination leads us to type 3. To prove the type 4 result, we need this lemma. And here is the type 4. This object being inferior to this object implies a positive difference evaluation function value, and the converse is true if both are delta compact. If delta is closed, A, B are delta compact and have lower continuous cut mappings, then this implies a positive difference evaluation function value, and a positive difference evaluation function value implies this one. Summarize, various types of Pythagorean fuzzy set relations based on a convex cone have been introduced as a new comparison criteria of Pythagorean fuzzy sets. Several results related to the correspondences between PFS and their difference evaluation functions have been obtained under the assumptions of certain compactness and continuity. They are useful in evaluate Pythagorean fuzzy sets with respect to multi-criteria comparison methods. Thank you very much for your attention, and here are some references used in the conduct of this study. Thank you very much, and if you have questions, clarifications, comments, suggestions, very much welcome.